All right, so 10.6 is parametric equations. We'll learn exactly what that is in a moment. But before we get there, what is cosine of 90?
Undefined. 1.
Cosine of 90, I'm sorry, is 0. Sorry. In my head was cosine of 0 for whatever reason. Cosine of 180. -1. Sorry, Ellie, I made her second guess herself. Sine of 0.
Oh no. 0?
This one's 0. This is the one that I was thinking of before. Okay. And sine of 270. -1. All right. Good. Cool. Thank you. All right. So a plane curve. Okay. First couple of slides are just screenshots from the textbook explaining kind of what we're doing, where we're headed. So up to this point, you have been representing a graph by a single equation involving two variables, right, such as x and y. In this section, though, we get to study situations in which it is useful to introduce a third variable to represent a curve in the plane. To see the usefulness of this procedure, we're going to consider the path of an object that is propelled into the air at an angle of 45 degrees. When the initial velocity of the object is 48 feet per second, it can be shown that the object follows the parabolic path. So traditionally, we would just look at this function as y equals x squared, negative x squared over 72 plus x. In this parametric section, though, not that the curve necessarily changes, but we can follow the path that the object goes on. So the original curve would tell you where the object has been. It does not tell you when the object was at that given point, x comma y on the path. So to determine this time, you can introduce that third variable t, which is called a parameter. Okay? And it is possible to write both x and y as functions of t to obtain parametric equations. So we're still representing the same curve, the same idea. But now we kind of bring that when to the table, okay? We can write this as x is equal to 24 square root of 2 times t, and we'll look at how that happens. And then y is equal to negative 16t squared plus 24 root 2t. So x and y with respect to time. We would then use values of t to input, and we can see that right here at time t equals 0, we start at 0, 0. And we move around when time is equal to 3 root 2 over 4, for example, or at 36, 18, etc. But it gives us kind of a direction, and it gives us a when answer to the question. Other key points. For this particular motion problem, x and y are both continuous functions of time, and therefore the resulting path is a plane curve. And just recalling that a continuous function is one whose graph has no breaks, holes, or gaps. So these are said to be equivalent, the rectangular form and the parametric form. The parametric form can be more helpful because it can give us more information in scenarios where a third parameter, such as time, could be helpful, or theta, an angle, could be helpful. So a definition of a plane curve: if f and g are continuous functions of t on an interval I, then the set of ordered pairs f of t comma g of t, or x and y of t's, is a plane curve C. The equations x equals f of t and y equals g of t are parametric equations for this plane curve C, and t is the parameter. Butterfly curve, this is just one of the common famous curves. It's a transcendental plane curve discovered by Temple H. Fay, and the curve is given by the following parametric equations. They're rather complicated, but if we looked from 0 all the way until 12 pi, we would follow a pattern, and there would be direction and all of that involved, and it would map that beautiful butterfly out with obviously those concentric wing petals they appear to be, and etc., using these parameters, right, these parametric equations. Okay, this is also in the note set for your reference. I'm not going to go through here too closely, but your calculator setup, you need to be in radian modes, you need to have the t-step settings, all are here, but you can refer back to this. It would be clearer on your own screen at home than it is right here on the screen up here. We'll go through this a little bit, but we're also going to take a look at just graphing them by hand, okay? But the calculator, of course, has this capability. All right, so let's get into the first example. Sketch the plane curve represented by parametric equations x equals t and y equals negative 2t. And t is defined from negative 2 until positive 2. Okay. All right, so you'll notice that the table of values has a third column now, the t, the parameter, the when kind of column, and then we plug that t into both x and y. We still plot x comma y on the rectangular plane as we always have, but we can label it according to the t, and again, it gives us direction. Are we increasing, are we decreasing, etc. So negative 2 to 2, we'll just use integers. Negative 2, negative 1, 0, 1, and 2. Those t's go into each the x and the y relationships, parameters. So x equals t in this case. Great, so all of them are exactly the same. So I'm just going to fill that in. I wouldn't normally do that. I would go one at a time, but since x is t, all of those are exactly the same. Y is negative 2t. So pulling from the t column, negative 2 times negative 2 gives me 4. Negative 2 times negative 1 gives me 2. Negative 2 times 0 is 0. Negative 2 times 1 is negative 2. Negative 2 times 2 is negative 4. So now I plot the x comma y ordered pairs, right? And I can label them as I show you here. So all of these I need basically just marking it out 4 times in all of the directions. So negative 2 comma 4 is the first ordered pair. It's right there. And I would label this when t is equal to negative 2. My next one is negative 1, 2. And this is when t is equal to negative 1. Then I have 0, 0. So t equals 0. Then we have 1, negative 2. T equals 1. And we have 2, negative 4. T equals 2. So this is linear, right? And you would put these arrows on there indicating the direction that we sketched that curve. We got from point t equaling negative 2, kind of like down to the next point, etc. When we keep on moving along, we'll get into like polar and things like that. And like that butterfly, you might map out more than one petal or more than one circle or what have you. And so that direction, of course, is going to be really important. Do you guys have questions? So these instructions say, eliminating the parameter. Sketch the curve represented by the equations by eliminating the parameter and adjusting the domain of the rectangular equation. All right, well, if I look at this as it's given, right, with the x and y, the parametric equations, what domain restriction might you put on t? Greater than 0. Good. It can't be 0. Can't be negative. It's got to be greater than 0. All right, so I would fill in this table. I probably would naturally start with 1, but then I'm going to realize that that won't give me the whole picture. If I picked 1, 2, 3, etc., the y is going to grow crazy, and I can't evaluate 1, 2, 3 nicely. I would have radicals in my denominator, so it doesn't help me. So then I was like, well, okay, let me go 1, 4, 9, 16, 20. Okay, now the y's are really going to grow like crazy, and I can't do it mentally. So wait a minute, circle back. Oh, greater than 0 doesn't mean the first integer. Greater than 0 could be 1/9. or 1/16, or 1/4, values like that. And that would be really, really telling into what goes on. So if I filled this table in and I said, let me work backwards. I don't want to have to deal with anything larger than a 9. So then I could go to a 4, I could go to a 1, I could go to a 1/4 and a 1/9, right? So work backwards. And then these values will be fine. So let's fill this table in using the parameters given. So if t is 1/9, x is 1 over square root 1/9, or 1 over 1/3, or 3. And y would be 2 times 1/9 squared, 2 times 1 over 81, so 2 over 81, whatever, small. 1/4, 1 over square root 1/4, 1 over 1/2, flip it, 2. 1/4 squared, 1/16 times a 2, 1/8. 1. 1 over square root 1, 2 times 1 squared, 2. 4. 1 over square root 4 is 1 over 2. 4 squared times 2, 32. 9. 1 over square root 9, 1 over 3. 2 times 81, 162. So I could plot this without even converting, right? We will convert, I want to obviously show you that, but I could still plot this. And then the key is to say, well, like, does this change my domain if I remove that parameter? Sometimes yes, sometimes no. But based on this, what do I have going on? At 3, which is where I start, roughly, right? I'm at something pretty small. Just put it right here. And we'll call this t equals a 9th. And then if I go to t equals a 4th, I'm at 2, and I'm a little bit bigger. So if I connected those, my arrow goes like to the left, basically, right? And then when I'm at t equals 1, I'm at 1 comma 2. Okay, getting better. When t equals 4, I'm at only a half, and I'm up at 32. So we can see the path of this. And then when t equals 9, I'm at a third, and I'm way up here at 162. So obviously not drawn to scale, but we can see what's happening there, right? And it would continue. Now, if I wanted to remove this parameter, though, what do you think I would do? How would I get t out of there? Yes, Akshay.
Like, just do the reverse of like whatever it is in the x and y like equation. So like if it's 1 over root t, do like root first equation over root t over t. I don't know. I can find it now, but I'm not really sure.
I think you're not seeing what the process would be for all of the time, but you're not wrong in saying reverse it. When we reverse it, we're solving for a different variable. So we want to think of this as a system of equations, where if I can solve for t in one of them and then put it into the other, then I'm good. Rule of thumb, if I can solve for t in my x equation and plug it into my y, that's the best case scenario, because then I'm already, y is isolated, I'm ready to graph it in a rectangular form. So that would be the goal each time. But there will be moments where it's like, it's just easier to solve the other one and then rewrite. So it'll be up to you a little bit. But if I take the x equaling 1 over root t, and then I say, well, if I solve this, I would first have root t times x equals 1, or root t equals 1 over x. And then I square it. So t equals 1 over x squared. So it is reversing what was going on. And then I take that and I input it, substitute it into the y parameter. and then I would have a y equation with no more parameter. So I would just have 2 over x to the 4th. Okay. What is my new domain restriction? Just 0. That's the only thing that's not allowed. Right? So if I added to this graph, this is like a rational function, I would have the same thing happening over there. Because now, instead of that square root, I have an even power. Everything's allowed, except 0 in the denominator. The positives and the negatives would give me a mirror image of one another. But I don't have direction. I wouldn't be able to say to myself, oh, wow, if time even made sense right now, but if I started small with my time, I would actually decrease in my x's and increase in my y's. And that would be giving me the same thing each time. What if we did something similar, but we did it with some trig? Sketch the curve represented by the equations by eliminating the parameter. Let's try to be tricky here. First of all, we can do that side work again. We can come up with our table, and it's 0 to 2 pi. Based on how the table is defined, I'm just going to go with 0, pi over 2, pi, 3 pi over 2, and a 2 pi. Okay? So if I put those thetas into my x and my y parameters, then 2 cosine at 0 would be 2. 2 sine at 0 would be 0. 2 cos at pi over 2, well, that would now be 0. And 2 sine at pi over 2 would be 2. Then when we go to pi, 2 cos at pi would be negative 2. 2 sine at pi would be 0. 2 cos at 3 pi over 2, 0. You can see the pattern, obviously. And 2 sine at 3 pi over 2, negative 2. 2 cos at 2 pi, back to positive 2. 2 sine at 2 pi, 0. So before we even think about removing this parameter and coming up with a rectangular equation, the sketch of this, if I just plot these points, right, with direction in mind, 2, 0, that's there, 0, 2, that's there, negative 2, 0, 0, negative 2, back to the beginning. What did I sketch? Well, it's not perfect, but what did I sketch? A circle. With my parameters, theta equaling 0, theta equaling pi over 2, theta equaling pi, and theta equaling 3 pi over 2, and ending with theta equaling 2 pi. So this is kind of the beginning of a polar graph. We're going to get there, but sort of like it. Okay? But yeah, we have a circle. Now, if I went about the same process that I did before, and I just said, well, let me take x and let me solve it for theta, I'm going to have this ugly cosine inverse of x over 2. And then I'm going to plug that into the other equation. Then I'm going to have 2 sine of cosine inverse of x over 2, which is just terrible, right? We don't like trig as it is, and then to have a sine and a cosine inverse and all that mixed together, right? We don't want that. We have a circle. What do we know about circles? What are their equations? Similar to ellipses that we just looked at, except for you know, like an ellipse is either stretched out vertically or stretched out horizontally. So a circle is more simply put x squared plus y squared equals r squared, right? It could have an h and a k, we could shift it for sure, but this one's not shifted. So our goal is to get to x squared plus y squared equals 2 squared, or 4, because I see that my radius is 2 based on just graphing it from parametrics, right? So I would even argue that graphing parametrics right here was really easy. Why would I want to even convert it? Well, sometimes solving in a rectangular is better, sometimes not. All right, well, how do I get there? What do we know in trig that kind of resembles that? What identity do we have in trig that kind of resembles that? The circle.
Cosine squared plus sine squared equals 1.
Perfect, thank you. Who said that? Is that Andy? Alan.
That's Alan.
Cool, thanks Alan. Yes, we know that cosine squared of theta plus sine squared of theta equals 1. Cool, well, we almost have that, right? If I take my x and my y parameters, well, x over 2 equals cosine theta, and y over 2 equals sine theta, right? So now I'm replacing the cos and the sine with the x over 2 and the y over 2. Whoops, I didn't mean to write a squared there. Hold on. X over 2, then squared, plus y over 2 squared equals 1. Great. We just have to take, it kind of looks like an ellipse right now, but the denominators are the same, so we can put that over to the r. So we have an x squared over 4 plus a y squared over 4 equals 1. So finally, x squared plus y squared equals 4. So when we begin with our parameters, x equals a cosine and y equals a sine, or, you know, it could even be vice versa. Think about a trig identity there. Can we convert this into a circle or perhaps an ellipse? And the graph would be the same thing here. And I would get the exact same circle, but if I graphed my circle, it would be just that, a circle. It wouldn't have any direction to it. With it being in parametric form with the theta, we go counterclockwise around the circle. At angle of 0, we're at 2, 0. At angle of pi over 2, now we're at 0, 2. Angle pi over 2 is up there. Then -2, so essentially we go around the circle. And we could continue that process, right, over and over and over again. All right, great. So this one is pretty similar, except now that coefficient in front of your cos and your sine are not the same. So what would you predict this one will end up being? An ellipse. Let's see. So let's do the parameters first, and then we'll convert it again. So 0 to 2 pi again. So there's our thetas that we're breaking this up to. So if I do 3 cos 0, I get 3. 4 sine 0, I get 0. 3 cos pi over 2, 0. 4 sine pi over 2, 4. 3 cos pi, -3. 4 sine pi, 0. 3 cos 3 pi over 2, 0. 4 sine 3 pi over 2, -4. 3 cos 2 pi back at 3. 4 sine 2 pi, 0. Okay. So if we plot these one at a time, 3 comma 0, and that occurs when theta is 0. and then 0, 4, a little bit taller. That occurs when theta is pi over 2. This is when theta is pi, and that's negative 3, 0. And then 0, negative 4 is down here. And then we do return over there. So this is when theta is 3 pi over 2. This is when theta is 2 pi again. So we are going in this direction. Okay, is that making sense for everybody? Oh no, low battery, 7%. Okay, hang in there, people at home. I hope I make it. I did a little bit more work during my break today. Like I said last time, if it crashes, then I will just pull you up on my iPad. All right. So we know we're going to get an ellipse. Now, how do we arrive there? Well, same way as before. Right? Isolate your cos. So x over 3 is cosine theta. Y over 4 is sine theta. Again, we know that cosine squared theta plus sine squared theta is 1. So we know that cos equals x over 3. So x over 3 squared. Sine equals y over 4. So y over 4 squared equals 1. That's the formula for an ellipse, right? X minus h quantity squared over your a or your b, depending on the major. So 3 squared or 9, whatever you want to write. And y squared over 4 squared. And so our major axis is vertical here. Our vertices, therefore, are then the 0, 4 and the 0, negative 4. But you can see how it all comes together there. Center at 0, 0. Okay. The next one is like silly easy, kind of. Kind of easy where you're like, oh, did I do something wrong? Because it's too easy. All right. Finding parametric equations for a graph. So if we are told that y equals 4x minus 3, right, that's our rectangular equation. Find a set of parametric equations using the following parameters. They tell us what t is equal to. T is x. Okay, well then if t is x, x is t, you can read that either way, then y is 4t minus 3. So literally our parameters, you can write them as an ordered pair, would be t, comma, 4t minus 3, right? X, comma, y. Or x of t, y of t. They told me that x was equal to t, so now all of my x coordinates are t's. They tell me y is equal to 4 times x minus 3. Well, x is just t, so 4t minus 3. That's it. The next one is a little bit better because you actually have to do a little bit of work in order to get there. So if t is equal to 2 minus x, well, x is equal to 2 minus t. Right? Just move those around. Okay. So there's my x parameter. I could put that in right off the bat if I wanted to. Then I take that 2 minus t and I put it in to the y parameter, 4 times 2 minus t minus 3, which is 8 minus 3, or 5 minus 4t. Yeah, that's correct. Okay. Any questions on that? I took the t equaling something, right? They tell us a parameter. I rewrite it so it's x equals. So I can do the substitution in the other direction, right? Put it into the y. So here's another example. Same process, same idea, but the other direction. We want to remove the t. Right now we are in parametric form. We want to remove the parameter and go back to rectangular. X equals 1 over square root t plus 1. Y equals t over t plus 1. Everybody try to take the left side, start with that, and solve it for t. Right, at the bottom here, you should get t equals. Then we're going to take that and put it into the y. While you're working, I'm going to switch over from my computer to my iPad because I feel like I'm going to lose you people. Which means I'm going to be turning the screen off, and I'll work through that with you guys somehow. But this is going to crash 4%. All right, so if I'm solving the parameter, does everybody here have the problem written down? Okay, so x equaling 1 over square root t plus 1. My first job was I'm going to multiply and switch the places of the x in the square root t plus 1. So root t plus 1 equals 1 over x. I'm going to square both sides, so t plus 1 equals 1 over x squared, and then subtract 1. So if I subtract 1, 1 over x squared minus 1. I want to write that now as a single term, so I could think of it as 1 over x squared minus x squared over x squared. So I would have 1 minus x squared over an x squared as my t. My t equals 1 minus x squared, all divided by x squared. So now I'm going to take that and put it into my y equation so I can remove my t. So y equals 1 minus x squared over x squared, all divided by 1 minus x squared over x squared plus a 1. So I have this messy complex fraction. So I'm going to multiply the whole thing by x squared over x squared, removing those little denominators, as I've always referred to them as. So my numerator would simplify to 1 minus x squared because the x squared in the denominator would cancel. My denominator would cancel to a 1 minus x squared. The over x squared part is gone, and then the plus 1 goes to an x squared, which is great because it goes to negative x squared, positive x squared on the bottom is gone. So I have 1 minus x squared over a 1. So this whole thing simplifies to y equals 1 minus x squared. All right, we have one more example for today's notes. A little bit of a challenge question, but it lends itself to some real life application. So I guess this is a part of history here, not so long ago. For you it might seem like a long time ago, but not for me. But anyways, in the annual Morton, Illinois pumpkin tossing contest, contestants used machines they built to throw pumpkins. So in 1998, an air cannon entrant set a record by throwing a pumpkin 4,491 feet. So we're going to take a look at another way that a pumpkin is thrown and see if we can come up with the total distance that this pumpkin got thrown. So anyways, parametric equations, this is the real world application, not just pumpkin throwing, can also be used to model nonlinear motion in a plane. For instance, consider an object that is projected into the air at an angle theta with an initial speed v. The object's parabolic path can be modeled with the parametric equations x equals v cosine theta times t. So v and cosine theta are going to end up being just constants coefficients. Velocity, the initial velocity, and the cosine of the angle that it's projected at, times t, plus x0, an initial x starting position, right? Commonly it's going to be 0. The y, how the height changes, is negative 1/2 gt squared. That's Galileo, right? That is just gravity. So depending on the units in the problem, it's going to simplify to a negative 16 or a negative 4.9 t squared. That's common. Then that in between, that middle term, v sine theta t, again, initial velocity sine based on the angle, and then plus y0, which would be the initial height. All right, so this example from the textbook, pumpkin tossing. So in a pumpkin tossing contest now in Morton, Illinois, a contestant won the catapult competition by using 2 telephone poles, huge rubber bands, and a power winch. Suppose the pumpkin was launched with an initial speed of 125 feet per second at an angle of 45 degrees and from an initial height of 25 feet. Write a set of parametric equations for the motion of the pumpkin. Okay, write a set of parametric equations for the motion of the pumpkin. All right, so just based on the definition of it from the previous slide, right, x equaling v cosine theta t plus x0. That's where this is going to come from. So x equals initial speed or velocity is 125. Speed is just the absolute value of velocity. Cosine of the theta, and they're telling us that that angle is 45 degrees, times t, plus an initial x distance, initial starting distance. So that's not indicated in the drawing, it's not indicated in the word problem, so that is a 0 for this problem. Right? It's like this ordered pair, we're looking for this distance is going to be our end answer, so we'll call this 0. Y, though, is not an initial position of 0. But the whole formula for y, well, we need our negative 1/2 g. Because the units are in feet, I'm using 32 for the gravity, t squared, plus speed, 125, sine theta, sine of 45, t, plus y0, initial height, which is 25 feet. Okay. So this pumpkin is, it's starting off back here technically, but then it gets launched and we're measuring it from the point that it releases from the poles that they built. All right, so we can simplify these both a little bit if you want to, but you don't really have to. Those are the equations. Part B, use the equations to find how far the pumpkin traveled. What do you think? What question can we answer to get to that final answer? Like, what's our thought process? How far does the pumpkin travel? Right here is where we need to get to. And that's going to be an x coordinate. X of t, comma, y of t. Is there a value that we know for that ordered pair right there? Yeah, good, Ellie. Y is 0 there. So if y is 0, then we can solve for when does that occur, right? At what time will y be 0? So we're going to take our y equation and set it equal to 0. So 0 equals negative 16 t squared plus 125, sine 45 is root 2 over 2, t, plus 25. The best way to solve this type of equation that I have found, other people use equation solver in your calculators. I always like to graph it. It gives me another visual. Graph it and look for your x-intercept. You don't have to type t's into your calculator. You can type x's. But what you'll find is the two x-intercepts occur at 0, right? Your initial starting for this parabola, which is actually negative because this pumpkin didn't launch from a height of 0. So therefore, the graph that we're putting into the calculator right here is not totally accurate to what the actual picture is. But anyways, the ending point, you'll find that t is equal to 5.794 seconds. And that is by graphing this in your calculator and looking at the x-intercept. I think I can pull it up. So if we know when it hits the ground, where do we then put that answer? Where do we put that t? If we want to know d, that horizontal distance in the x equation, great. So x of 5.794 is 125 root 2 over 2 times the 5.794. Total distance 512, 122 thousandths